Yo, what's up? Saturday night, uh, 27th of March, and I am obsessed with trees. What can I tell you? I have another tree problem for you, okay? I'm gonna have so many tree problems that I'm gonna have a forest by the time I'm done. But remember, trees are good because they're good for the environment. Actually, these trees are probably not good for the environment because I'm using electricity to construct these trees. But maybe they are good because maybe one day I'll plant some real trees and because I'm so inspired by these digital trees that I'm building. Anyway, let's get to the problem. So, tonight I have an interesting problem for you, and I'll get to why it's interesting in a bit, but the problem is called delete leaves with a given value. Okay? It's a medium on LeetCode, and people really seem to like it a lot. 670 likes versus 15 dislikes. And I bet the dislikes are tree haters. Anyway, so the problem is, given a binary tree root and an integer target, delete all the leaf nodes with the value target. Notice that once you delete a leaf node with the value target, if the parent node becomes a leaf node and has the value target, it should be deleted. You need to continue doing that until you can. So this is interesting because at first you might think, well, all I need to do is just delete anything that's a leaf, and that's pretty easy. That's just going through a tree and getting rid of anything that doesn't have a child, left child, and a right child that happens to have a target value. But then, as the tree modifies, it folds up as you delete more leaves. Uh, nodes that you've already uh, nodes that you've already traversed that had children that were leaves that were deleted may become leaves themselves, and then you have to take care of those, and then you have to recursively take care of those. So the tree has to be modified on multiple levels from your DFS. So you can't just do one. Essentially, you just can't have one deletion cycle. You'll have to figure out a way to have several deletion cycles. Now, conceptually, this may not sound so complicated in the sense that, well, why don't we just do a DFS, get to the leaves, then keep doing a DFS until we have no more leaves? Just repeatedly do a DFS traversals. Now, I'll say this much, that's probably an inefficient way of doing things, right? Because you're going to have to keep traversing the tree multiple times until all the leaf nodes are deleted. You can do that, certainly, but if you're in an interview or something like that, if your tree is humongous, if you have a practical situation where you have a tree that you need to repeatedly search over and over again after you've deleted the leaves for a leaf, then for new leaves, and move them, then you can imagine that will not scale because it will be something on the order of n squared, right? It's like essentially a geometric progression rather than um, a one pass situation. And you're thinking, can you do this in one pass, right? Well, I'm here tonight to show you that you can actually do this in one pass, right? Let me show you how you can do that in one pass. Okay, so this is my solution. There's probably others. Let's start with the classical DFS, okay? Well, we're always going to have a DFS, right? Void DFS, okay. In the DFS, I'm going to obviously have my tree node, root, and because I want to delete a leaf from the tree, I'm going to have a reference to the parent. I'll explain this in a bit. Also, I want to know if the thing that I'm deleting is the left node or the right node, right? So to make it easy for myself, I'm just going to pass that through the tree, and I'll call the indicator a Boolean, whether it's left or right, and I'll pass my target through the tree. Okay, so normally, and you've seen me do this before, what I do is I typically do pre-order traversals. Okay, that's the most common kind of traversal, and in-order traversal is a natural type of traversal if you want to go through the tree and it's a binary tree and you want to go through the nodes in an ordered fashion. But this time, remember, there's one other type of traversal that's very common to trees, and that's the post-order traversal. You have pre-order, in-order, and post-order. Right now, I'm going to be telling you that the way that you want to solve this is through a post-order traversal. And what does that mean? So that means normally in a pre-order traversal, right? Well, we first always check, do our check, our food equals null, return, because I'm not going to do anything here, right? Absolute base case. Now, normally we do some work, then we do DFS left, DFS right. Okay, so that would be a pre-order traversal. And why is it a pre-order? Because we get to the work before we do the traversal. And recursively, if you unfold the stack frames of this tree traversal, you'll see that that's what it is. You always do work, you do work, do work, traverse, do work, traverse, do work, traverse. What we want to do is actually, we want to traverse all the way to the leaf nodes first, right? Can we get to the leaf nodes? And then can we sort of go up the tree instead of take care of the work and then traverse down the tree? Why do we want to do that? Because that way, when we get to the leaf nodes, we can prune the leaves, and we know the state of the tree after it's been pruned as we fold up the tree. So we're not going down the tree, pruning, then going down the next tree and pruning, because we don't know at that point like how far down we'll have to go before we get to the leaf nodes in order to prune, right? In this way, we can sort of work our way from the bottom and go up the tree as we modify it, so we can take care of leaves successively after we fully recursed through each of the steps. It might take a little while to understand, but you'll get it. So let me show you how I handle this. DFS root. So what I'm going to do is I'm going to traverse the tree first, right? And what that entails is DFS root.left, root, true, target, and then I'm going to do DFS root.right, and that I'm going to set the value to false, okay? So I'm going to traverse to the left and right portion of this tree now, and the next step, what I want to do is the actual work. So how do I prune the leaves? If root.left equals null and root.right equals null and target equals root.val. So this is all the conditions you need in order to actually prune a tree. You need the target equal to the target that was indicated when the function was called. You need the node to be a leaf. So these two conditions here make sure that the node is a leaf. Okay, and if parent is not equal to null, because remember we're going to have to take care of the root, the absolute root of the tree, not just roots that are generated deeper in the tree. Like we have to, and the tree starts out, the first root has a null parent. It has no parent since it's the top level of the tree by definition. And then we check if the tree is null, parent.left equals null. So this is the point where we're actually doing the prune. Parent.right equals null, right? So and this is why I wanted a reference to the parent, okay? Because the parent is going to be the only way to know how to remove the reference. It's the only thing with the actual reference. If we set the left or right node to null, that won't do anything, right? And we don't, root.left and root.null right are not what we want to set to null. That's just how we know that we have a leaf. The current root is a leaf. But otherwise, we have no reference to the root. In order to eliminate the root, we'll have to eliminate the leaf, which is the current root. We'll need some reference to it, and that's why we kept the parent, okay, for that convenience. Okay, and then what we want to do is call our main function. DFS root null false target. Okay, and it should be as easy as that, right? Return root. Well, let's see. just make sure we have everything right here. Oh, this should be int. I believe we're passing an int target. Say, that'll look right. Now let's try to submit and see what happens. And whoops, we have this situation. So what happened here? What happened here? Why is this the wrong answer? We should have been able to clear out all the nodes, and this is pretty much a tree with a one left node, one right node, and one absolute root all equal to 1. So this should have deleted all the trees. Remember what we just said about the references. Okay, the reference is important. We can delete all the nodes, but you see, finally at the end, what's left is the absolute root. And we're not taking care of the absolute root because we have no condition to delete the absolute root. So how do we delete the absolute root? Well, we could do what if we did something like this? Root equals null. Well, that won't do anything, right? Because, let's try it. Of course, that won't do anything because remember, root equals null is just a local reference. We're not deleting any attached reference by doing that. That just happens to be the value that we pass by reference. Setting that reference equals to null just by the variable name itself. You're just sending a reference equals to null. So how do we take care of this situation? Well, in order to handle this, we can deal with the root directly. If root not equals null and root.left equals null and root.right equals null and root.val equals target, then return null. And otherwise, we're just returning the root, okay? And lo and behold, that seemed to work for that case. Let's see, does it work for everything else? And yes, it works for everything else, and overall it looks like the algorithm was pretty good. It worked against how many test cases? It worked against all 50 test cases, great. And it was faster than 100% of Java submissions, yes. And the memory was 87.52%. That's probably because I did this recursively, and I could have probably done this through an iterative process. But whatever the case, it worked, and the runtime of this was approximately O of n. Now again, the runtime would have been O of n squared, on the order of O of n squared, right? And we can do a proof of that using Gauss's method, left and right, the one that he said to have made when he was a child of integers multiplication. But we don't have to do that because we can kind of guess that we're traversing the tree at most a square iteration if we're going to do some kind of pre-order traversal, as opposed to this post-order traversal that we did. We don't have to keep going from the top to the bottom of the tree over and over again. Is that what I'm trying to say? As if we were to do a pre-order traversal, we would have to do that. In this case, we go down once to the bottom of the tree, then we fold our way upwards and prune as the recursion steps end, okay, by doing the work at the end of the tree. It's important to know the difference between pre-order and post-order traversal and when to use it effectively to make your solution efficient. Okay, well that's it for this video. If you like this video, subscribe, leave some comments below, and don't forget to follow me, and if you have any questions, confusions, ask me, and I'll do my best to help you out. Have a good night, and happy coding.